coming to a still higher level of abstraction, the third one, the substance field diagram that I talked to you about. See, in mathematics, we have this language of algebra. In chemistry, we have chemical equations. In semiconductor physics, we talk of band diagrams. So Altshuler said, let me define a language for inventive problem solving also. So he came up with this, he utilized the learning from mathematics and said that, okay, I have to go to a higher level of abstraction to find solutions. He now said that just like they use a language, why can't we use a language in inventive problem solving? And he defined what is called as a substance field diagram. He said that typically there would be interactions between substances which could be insufficient or harmful, and therefore any problem would exist in the first place. By correcting the substance field diagrams, we could handle all the problems that the system is experiencing. Okay. And he said the kinds of fields that you could use could be mechanical, thermal, chemical, electrical, magnetic, optical, acoustic, and so on. So he listed these fields also, which could be used to solve the problems. In fact, what he did was, okay, so let's look at an example of how this works. Let us say this again was a real problem. This was a factory where steel ball bearings were being manufactured. Okay. Now, in a factory setup, in a factory shaft floor, you would create something in one area and you would transfer it to the other part of the shaft floor. So these steel ball bearings were to be transported from the place where they were kind of made to another place where they would be packaged or they would be polished or something like that, let us say. But this movement is required. This movement was being done by using steel pipes. Now, what was noticed was that wherever there were bends in the pipe, the pipe would break every 2 months. And then you would have to halt the production. You will have to change the pipe and then restart the production. So it resulted in loss of time. It resulted in extra cost because you have to change pipes every 2 months. So what would you do if you were in this place?
So
instead of air,
we could add some strong material on the like over the bending of the pipe so that it can't break.
Okay, so Anuj, what you're telling us is you are using the principle of local quality. Only where the pipe is bending, I would make the material stronger so that I do not increase the overall cost, but I improve the life. Am I right?
Yes.
So this principle is called local quality, inventive principle of local quality. Great. But now instead of 2 months, the system would fail after 6 months.
Okay.
Sir,
I've improvised it, but it will still fail. What else can we do?
The way we can change the way in which the ball's trajectory, it moves.
How do you do that?
Like some other kind of bend. No.
That would mean more shaft floor area.
Or maybe because they are steel balls, they can roll over themselves to the side where they're supposed to go.
So using so you're saying
We
that
can
let
just
them simply roll over.
Yeah, we can just have like a sliding, like a passage, and they can just roll over.
But what if my shaft floor was only one floor and there was no that potential energy or something available with me? So in fact, this is a good idea. We could use it in some places, but in this place, it was not possible.
I was thinking maybe the corner with some shock absorbing materials. We can insulate the corner with that.
Yeah, again, local quality. But as I said, with local quality, the problem is after some time it would fail.
Sir, we can make the corners movable. Like if we have to change it also that like it wears out, then we can directly remove it and install new one instead of removing the whole pipe.
Okay, so you segment it so that you replace only that particular part.
Yes.
So
sir.
the cost factor you're taken care of, though you will still need to halt production every 2 months or 6 months.
Instead of air plus steel balls, we could have used water plus steel balls. Like it could avoid the damage, direct damage to the walls.
So you're using a material intermediary so that the balls would slow down before they hit the wall, and therefore the damage would reduce. So this principle is intermediary. Great, I'm happy. See, without even using the technical contradiction matrix, you are already thinking on using those principles that we just talked about.
So since you have, for example, put the heading as self-service, so I mean it would be using some kind of the parts wall itself, maybe. Like maybe uh, I mean the moving parts or the balls. Maybe you are. I mean you within the system it generates a solution kind of that. Maybe you are looking into. I'm not able to conclude solution maybe, but
Yeah.
just.
So thank you,
Maybe
Raghav, for
kind of.
taking us in that direction. But Srijan and Saurav, Shubham, I see your hands also raised. Do you want to add something?
Sir, like we could work on like when the ball bearings are moving and the corners, we could try to decrease its speed, like applying air pressure in the opposite direction, so that its speed decreases at the corners.
Yeah. So yes, intermediary again, high pressure air channel there. Some extra cost in getting those channels in every bend that you may have on the shaft floor. But yeah, good idea. Soumyadeep?
So we can interchange the movable parts, like the balls, the bearings are movable, so we can keep them at resting, and instead we can have the pipe like a conveyor belt to be movable.
Okay. So with the steel balls, the problem is that they will simply roll off the conveyor belt also, Soumyadeep.
Okay.
They're ball bearing.
Maybe we can cushion these steel balls with some foam so that they do not.
Every steel
after
ball
impact.
will put a foam. So उससे better तो फिर वो intermediate. So you're also talking about adding an intermediary. The ball and the wall, they interact through an intermediary. That is what you're saying. But
Yeah.
Covering every ball with a foam,
So maybe we can put a cushioning foam on the bends only so that they reduce.
yeah. So that is again local quality. The foam would also wear off after some time, and then you will, instead of 6 months, you will need to replace by 7 months.
That's true.
So local quality का ये challenge रहेगा. Devjit?
Sir, instead of using such a sharp bend, we can increase the arc of the bend, sir. So
yeah, that was also shared earlier. So we talked about we would need more area on the shaft floor then.
Okay. Yes.
Jaskirat?
Using some kind of a principle of viscosity here, like the honey, like if you are talking about self-service, like the honey, when when we put honey on a surface, like lower surface moves slowly and upper one moves fast. So similar principle, like kind of a similar principle here also.
Okay, yeah. So again, honey or viscosity is like using an intermediary or a different medium where, for example, the example of water had also come earlier. So great. Great ideas, but there is a simpler solution, much simpler and cheaper solution. See, when you use a honey or some other intermediary, what happens? The balls would also move slow everywhere else, not just close to the bend. They will move slow everywhere else.
Not honey as an intermediary, like steel balls themselves creating a same kind of viscosity effect here, like just trying
Steel
to
balls
feel
and
like
viscous. Steel balls are solids.
no means like effect like similar kind of effect, like you're mentioning it's that they are kind of doing a self-service or something, so that's why.
Okay, so there could be some scientific principle which we could use to have steel balls move like a viscous liquid.
So I have one idea.
Yeah.
Maybe we can, instead of using a bend, just use two straight pipes and collect the balls at each end and throw them at the other end of the other pipe.
Oh, so what happens is that this pipe was actually running on the roof of the shaft floor.
Okay.
So they will fall every time, they would get damaged, all that would happen. So, okay, let us see if there is a simpler, much simpler answer by using the substance field diagrams. So what is happening is there are two materials, steel balls and the ball, and they are interacting with each other, but they are interacting freely. There is no field which controls their interaction. All the kinetic energy that these balls have, when they hit the wall, they transfer it to the wall, and therefore they damage the wall. Am I right? That is what is happening. So there are this S1 and S2 interaction where there is no field which controls their interaction. A field is missing. What field would you want to add? Now, since we're talking about steel, a very obvious choice could be magnetic field. So what is done is we put a magnet on this bend. Now what happens? The steel balls come and actually attach themselves to the wall of the pipe. Now, new set of balls are coming from behind. They may hit now only these balls. They will not hit the wall now. The balls, they have more than one surface point in which they are in contact with other materials. So balls are in touch with each other, and the balls are also in touch with the wall. Instead of transmitting all the kinetic energy that was transferred to these balls would now transmit it to other balls also. And as a consequence, the overall impact on the walls would reduce. When the impact of an incoming ball is very strong and the ball bearing which was attached to the wall because of magnetic force falls away, let us say, the new ball which had come would actually get attached itself there. So the balls themselves are protecting the wall from other balls. Are you able to see this?
Sir, but won't this lead to wastage of some steel balls because they would be stuck? They would be stuck to the magnet.
Okay. How many balls would be stuck? 20 balls? 100 balls? How many balls are you
Depends.
manufacturing on a daily basis? Thousands.
Okay.
Sir, won't the balls accelerate while approaching the bend again?
Because there is a magnet there?
Yes, sir.
But they will now, so you can actually, they will now hit other balls only. Even if they accelerate a bit, they will only hit other balls.
Sir, won't the
But
magnet also break sometime?
Magnet is outside the pipe.
Sir, we can
Oh.
use electromagnets like electric currents to charge
Yes.
the coil.
So how now which magnet to use is the substantiation of the solution, the third stage. Okay. See, when you were applying these principles, I was telling what could the problem be. They were the secondary problems that were coming. So, you know, abhi jab hum ye ideation hi kar rahe the, we were moving from problem identification to solution identification to concept substantiation. Did you realize this? We were doing this. We were going through all the three phases when we were talking about the solution to this problem. Did you realize this?
Yes.
So, अब हम किस तरह का magnet use करें? That is again concept substantiation. What works? What is readily available there? We will use that material.
Also, a doubt.
Yeah.
So initially, the problem was that the balls were hitting the line, the pipe,
The wall.
but due to which it was getting damaged. So now, when the balls are hitting the other balls, even those balls will get damaged, right?
But look at it like this. How many balls would hit any particular ball? 10, 20. उसके बाद तो ये वाली ball हिल के आगे move कर जाएगी. But the pipe would see the impact of thousands of balls. We're always talking about steel. 10 times hitting a steel ball would not damage it, but 1,000 times hitting it would definitely damage it.
Right.
Are you able to see this?
Yeah.
But
So instead,
yeah.
Here
so
also
instead of like, yeah, please go ahead.
Here also the impact of the force is getting reduced because the balls are, instead of hitting the pipes, are hitting the other balls. So it's not that the force is completely gone; it's being reduced. So now won't the pipe be broken after, instead of 2 months, 6 or 8 months?
So in fact, the solution actually was so efficient for them that they realized that the life of the pipe actually extended by 10 times. Okay, and at almost zero cost. And then you would apply all those other principles of segmentation so that we only change the bend and everything else also. All those things you could do. But the point that I want to putting forward is that by using this higher level of abstraction, they were able to arrive at a much better solution. By just completing the substance field diagram, they could arrive at that. Okay. So it's a very powerful method actually. In fact, it is so powerful that these two problems are also similar. So hydrofoil, do you know what a hydrofoil is?
Which
No.
is water repellent.
No, not a hydrophobe. It's a hydrofoil. So it's a kind of a boat which kind of runs on the surface of water. So you see this photo on the left. You see the entire boat is outside of water. Are you able to see this? So when you're running this boat, the entire boat is almost outside the water. So there is almost zero drag coming from water. And you can actually move very, very fast. So the way the hydrofoils are designed, they have this, with these such kind of boats are designed, they have this hydrofoil at the bottom, which is the only substance interacting with water. So the surface area has reduced very significantly. And because they move at very high speed, they generate lots of air bubbles. You can see the air bubbles in the photograph also. What happens is these air bubbles start to cavitate into this material, and after some time, these hydrofoils have to be replaced. This is one problem. Another problem is that monkeys love oranges, and they kind of just enter into orange orchards and spoil them, completely, cause havoc, and they reduce yield very significantly. We want to handle this problem. So there are these two problems which appear to be so different, but for TRIZ, they're actually very similar. For TRIZ, in substance field diagrams, there are two substances, air bubbles and hydrofoil, and in the other place, monkeys and orange orchards, which are interacting in a harmful manner. Are you able to see this?
Yes, sir.
Two completely different problems, but when we went to the substance field diagrams, the substance field diagram is exactly the same. And the solution for such substance field diagrams is also exactly the same. And the solution is introduce a modification of either substance 1 or substance 2 when they interact. For example, freeze the water at the surface of the hydrofoil by running a refrigerant through the hydrofoil. What happens? Now there is a thin layer of ice at the hydrofoil. Air bubbles come, but they cavitate only the ice, not the hydrofoil now. Okay. And if they cavitate some part of the ice there, we are already running in water, more ice, and the refrigerant is already moving. So more ice would automatically get there. So it gets regenerated and our hydrofoils remain intact. In terms of orange orchards, you surround those plantations with lemon trees. Lemons are sour. Monkeys don't like them. They will assume this is a lemon plantation, not an orange plantation. They will not even enter your plantation. Another solution that we use in India very often to handle monkey problem is a modification of monkeys, which is langurs. Langurs just do not let monkeys come near you. Just one langur will keep hundreds of monkeys away from your plantation there. Oh, okay, you have to handle a langur though. So it's not an easy thing to handle anyways. But you see, the solution is also, the concept of the solution is also exactly the same. This is the power of standard solutions or